When we dilute a solution, if we're using molarity, it's a very simple process. Since molarity times volume is equal to moles, if we take a small amount of a concentrated solution and add more solvent, we're not going to be changing the moles of the solute. So we take a small amount of a concentrated solution, molarity times volume will give us moles of the solute. We add more solvent, we're going to add the same amount of solute, moles, but we're going to have a larger volume and a smaller concentration. So we end up with the equation molarity times volume equals molarity times volume. M1V1 equals M2V2. So if we have a 12 molar hydrochloric acid solution, this is how it's sold, that's concentrated hydrochloric acid solution. We want to make a liter of a 3 molar solution. We need to determine how much of the 12 molar solution to measure out that we dilute to 1 liter. So we take the equation M1V1 equals M2V2, solve for volume V2, so that'll be our concentrated volume. So our diluted volume is 1,000 milliliters times our diluted concentration 3 molar divided by concentrated concentration. We'll end up with 250 milliliters of the concentrated solution that we need to dilute to 1 liter to make a 3 molar solution. When we talk about solubility, we can talk in qualitative terms, whether something is soluble or insoluble. And soluble means something dissolves to a significant extent. Insoluble means that something does not dissolve to a significant extent. So soluble is significant, insoluble is insignificant. And the level of significance depends upon our purposes at the times. When we say that something is insoluble, it does not mean that nothing dissolves. Generally, a small amount can dissolve of pretty much everything. When we talk two liquids that dissolve in each other at any concentration are called to be miscible. So water and alcohol, we can have a drop of alcohol and water, or we can have a drop of water and alcohol, we can have half and half, and they all stay mixed together. Liquids that will separate into separate layers are called immiscible. So that would be salad dressing, vinegar and oil. These will separate back out unless you have a good emulsifier in there. We can also make solubility quantitative, which is usually what we want to do. So we give an amount of solute that can dissolve in 100 milliliters of solvent. That's our standard way of specifying solubility. And for liquids and solids, solubility generally increases with increasing temperature. But the way it increases can vary significantly. So for solubility of sucrose in water at 50 degrees, solubility of sucrose would be 130 grams of sucrose per 100 grams of water. So it can be a very concentrated solution. The line in this graph represents a saturated solution. This is as much as we can dissolve into this water at any particular time. So in that graph, anything underneath the line would be an unsaturated solution. That means we could dissolve more into it. Anything on the line would be saturated. And then occasionally we can get into a supersaturated state where we have a A larger amount then is stable. It's can be a metastable solution. It can remain liquid sometimes for a long period of time until something initiates the crystallization process, such as a seed crystal, maybe a bump, stirring, or in one commercial product, the flicking of a piece of metal. And then once the crystallization process starts, all the excess material will precipitate out of solution, leaving us with a saturated solution. The general way that we know that we have a saturated solution is that we have some solid that will not dissolve. If we have solid that will not dissolve, we have a saturated solution. So generally, if we have a strong solvent-solute interaction, we'll have a higher solubility. On this graph here, we can see that we have some wide variation. Potassium sulfate increases only slowly with temperatures. Silver nitrate increases dramatically with temperature. No, some of the lines look linear, other lines look curved or potentially exponential. Then we have some compounds that change solubility. The examples here are ones that are hydrates that change the hydration number as the solubility or the temperature changes. And some even have a negative solubility with temperature. So sodium sulfate decreases in solubility as we increase our temperature. So polar solvents tend to dissolve polar solutes. So some polar compounds, water is our most common one. Alcohols, ethanol, or isopropyl alcohol, methanol, acetic acid, vinegar. Nonpolar solvents would include gasoline, diesel, paint solvent, naphtha, petroleum naphtha, carbon tetrachloride, hexane, diethyl ether. Most organic compounds, most all hydrocarbons that contain only hydrogen and carbon are nonpolar. Most organic compounds that contain oxygen are polar. Ether is a category of oxygen-containing organic compounds that are so mildly polar that they behave mostly nonpolar. We have the like dissolves like rule, that two compounds dissolve if they are of similar polarity. So polar compounds will dissolve polar solutes. Nonpolar solvents will dissolve nonpolar solutes. Then polar solvents will dissolve ionic compounds, at least some of them, because polar is a partial charge separation, ionic is a complete charge separation. So they share a charge separation that allows them to dissolve each other. Nothing new there. So, I've said this before, the solubility of most solids or liquids increase as we increase temperature. And the curves can be drastically different, linear with low slopes, high slopes, or it can be exponential. Gases, on the other hand, the solubility of gases decrease with increasing temperature. We have a number of compounds that are gas dissolved in water, from soda water, carbonic acid. A number of our acids are gases dissolved in water. Hydrochloric acid is hydrogen chloride dissolved in water. Sulfuric acid is sulfur trioxide dissolved in water. We can quantify or predict our solubility of a gas in water using Henry's law. Henry's law is that the solubility of a gas in a liquid is proportional to the partial pressure of the gas over the liquid. So our concentration is equal to a constant times the partial pressure of the gas. And the constant will be for the particular combination of the solute, the gas, and the liquid, the solvent. Some examples of Henry's law constants. Ammonia is our largest one in this list, 58. So we can dissolve a large amount of ammonia in water. Carbon dioxide, 3.4 times 10 to the minus 2. So to get carbon dioxide into water for soda water, we need a higher concentration of carbon dioxide over the water. But it also means that as we release that pressure, the carbon dioxide comes back out of the water. Solubility of oxygen is even less, 1.3 times 10 to the minus 3. And nitrogen is even less from there, 6.1 times 10 to the minus 4. We do not have to memorize these constants.